You are able to see my screen, right?
Yes, sir.
Yes, sir.
Okay. So in the last class, we have looked at this fact that Kf is smaller than Kt. That means fatigue stress concentration factor is smaller than theoretical stress concentration factor because of the local plasticity that is observed in the material, and hence crack becomes less dangerous than when you have no plastic zone. So now let us look at, so basically you need to know how to deal with fatigue failure when you have a system with notches or reduction in cross section and so on. Here you have a rectangular stepped shaft bar shown in figure to be loaded in bending. Determine the fatigue stress concentration factor of the given dimensions. For this D equal to 2, D equal to 1.8, R equal to 0.25, SUT is equal to 100 kpsi. How do you do that? Kt, the theoretical stress concentration factor, we have seen when we have studied static failure theories, you can see A R by D whole power B. And by going to those uh, formula, you can find for this R and D, A and B can be found, and then for the SUT corresponding to an SUT of that, then this will be your theoretical stress concentration factor. And notch sensitivity factor depends on radius as well as the ultimate tensile strength. Based on this, you will be able to calculate A. From that, you can calculate Q, that is what we call notch sensitivity factor. Once you have a notch sensitivity, you can calculate Kf. So first you need to calculate Kt, which depends on the dimensions. Okay. So this is typically what you would realize is that Kf in that case will be smaller than Kt. So now let us look at this particular problem. So you have a circular cross section whose diameter of the shaft is 12.7 mm, and there is a cut with a notch radius of 0.4 mm. So let us say this is a rotating beam bending member as shown in this figure, whose ultimate strength is 450 MPa. Now for this particular configuration, you need to find out Kt and Kf. After finding Kt and Kf, we need to find what is the estimated completely reversed bending moment. That means what is the bending moment amplitude that we can apply so that the life is 10 power 6 cycles. Okay, that is the question that we need to address. So for this, if you look at this figure, for a notch radius of 0.4 mm, 0.1, 0.3, 0.4, your Kt will be something, Kf will be something. You can directly read from this graph, or because you know this is fully reversed bending, right? When the rotating beam bending, it is completely fully reversed bending. That means this is the loading scenario. For pure bending, if it is D2 and that is D1, let's say rho is notch radius, then you need to find out what is my Kt. So what is D1 in the previous case? D1 is 12. So if you look at this fellow, this outer diameter is D2, this is D1, right? So 1.27 times 2 is 2.54. 12.7 minus 2.54 will be your small d1. So d2 is 12.7. Notch radius is 0.4 mm. d1 is equal to 12.7 minus 2 times, because this distance is 1.27 is given in the previous graph. So previous picture. So d1 is 10.6 mm. By knowing d1 and rho being 0.4, 0.4 by 10.6 is what? 0.0394. That will be somewhere here. 0.025, 0.0394 is somewhere here, right? Correspond, and d2 by d1, one of these graphs, that is 1.25, this is 1.45, 1.02, 1.11, and this is 1.45. So that means 1.25 is somewhere in between, right? And corresponding to that, you have to calculate this and then find out Kt. So from the graph, you will find out this Kt is somewhere 2.6, 2.7, depending upon the value. If you calculate Kt is equal to 2.7, Kf is equal to 1 plus Q times Kt minus 1. Q is your notch sensitivity, depending upon the ultimate strength of the material being 450 MPa. notch radius rho being 0.4, one can compute Q from the Neuber's constant, and that found out to be 0.55. I have not calculated it, but you can look at if you look at this notch radius point, not 4 mm, and this is how much? 414 is what you can. So the second one is 414. It is about 0.04. Notch radius is how much? 0.4 mm, not 0.04, 0.4 mm and 450 MPa. To notch radius is here 0.2. 0.4 mm is somewhere here. This is mm and it is in inches. That is why you should not look at it. 0.4 mm. So that is somewhere here. And 450 MPa. 450 means somewhere the second and third line from the bottom. So because this line is 345 MPa, 414 MPa, 480 MPa. So between the second and third, so 0.4 between the second and third, somewhere here. So that is why it is 0.55. So you can look at that, and then from there you calculate it to be 0.55. KT is taken from this graph 2.7. So KF is 1.935. The fatigue stress concentration factor is 1.935. And at 10 power 6 cycles means 1 million cycles. Then the fatigue limit is SE 0.5 times SUT. That will be 225 MPa. At 10 power 6 cycles, because it's 0.5 SUT, it should be 225 MPa. Corresponding to 225 MPa, what is my M? So this S is given by 225 MPa. And therefore, the allowable stress amplitude for a life of 10 power 6 cycles will be sigma F is equal to SE by KF. You have to take into account of this. That is 225 by 1.935, 114.1 MPa. And you plug that into this equation, because that is 114 MPa. And then you will calculate M. So the bending moment that corresponds to 10 power 6 cycles in this scenario is 11.74 Newton meter. Please note that if you have taken 225 MPa, you would have computed this to be much larger number. But there is a fatigue stress concentration factor. You need to account for that. And hence the actual stress that you can apply will be much smaller than what you would have had without this notch. This is without notch. Once you have the without the notch and then take stress concentration factor into account, then this is the actual stress that the material can withstand, stress amplitude that the material can withstand. Corresponding to that stress amplitude, what will be the moment is what we bending moment amplitude that we have computed. That is 11.74 Newton meter. Okay. Any questions here? Any questions?
Yes, sir.
Yeah. Okay. So now, so suppose just now we have seen effect of notch, but we have not taken into account of the mean stress. But if you take account of notch in the presence of mean stress, what you have to do is the values in empirical relations given for KF are usually given for the case of zero mean stress. The simplest approach is Goodman relation with nominal stresses. So Goodman equation for notched members will be as simple as that. So SM by SUT plus SA by SAR equal to 1. So sigma AR by KF. Instead of SAR, you will write sigma AR by KF. You will introduce fatigue stress concentration factor. And if it is 1, that means there is no fatigue stress concentration factor. That means sigma AR by SA. Or what was the equation that we are writing earlier? Sigma A. Sigma A by SF. SAR, SF, both of same. Sigma A by, or SA by sigma A will become sigma A by KF. This is the way that you account for fatigue stress concentration factor. Okay. For this is for ductile materials. For brittle materials, you also have to take into account of the fatigue stress concentration factor even on the mean stress. For ductile materials, you don't take into account of fatigue stress concentration factor on the mean stress. Because here this equation implies that the notch factor mean stress is 1. Notch factor for mean stress. However, for less ductile materials, if you have a brittle material, there will not be any redistribution of stress ahead of the crack tip, and hence mean stress also should take into account of the notch factor. That is why if you are dealing with a brittle material, you have to have a effect of Kf taken both for mean stress as well as alternating stress. Okay? But the fatigue stress concentration factor for mean stress and alternating stress are usually the same. You will take them to be equal unless it is mentioned in a particular problem. Okay? So if you have a smooth specimen, that's how it looks like. And if it is a ductile material, there is no fatigue stress concentration factor effect on the ultimate strength, but there will be fatigue stress concentration factor effect on the stress amplitude. That is why sigma AR by Kf will come here. So this will be for ductile material. If you are talking about a brittle material, there should be fatigue stress concentration factor effect on this, and hence sigma U will become sigma U by Kf. Sigma SF becomes SF by Kf. Right? If you look at our equations that we have written, give me a minute, I will go back to our equations so that the terminology is not confusing to you. So all that we are doing is the following. If I have to redo that for you, today is first. Right? So for this particular figure, that is my SF, that is my SUT, and this is sigma M, and that is my sigma A axis. Then if that is my Goodman line, right? Sigma M by SUT plus sigma A by SF equal to 1. Now, for a brittle material, for a ductile material, you don't have effect of mean stress on the effect of fatigue stress concentration factor on the mean stress, right? Only on the SF. So, sigma M by SUT plus sigma A by SF by KF is equal to 1. Because KF is greater than 1, SF by KF will be less than SF. So that I am calling as SF dash. That is equal to SF by KF. Right? That implies sigma M by SUT. So that means my new equation would become my new failure line will be sigma M by SUT plus KF sigma A by SF equal to 1. Right? Any question there? Now, if I am also, suppose if I am talking about brittle material, then there will be effect on the mean stress also. Then this becomes SUT dash, that is equal to SUT by KF. Right? Then my equation would become my failure line will become this, right? So this is smooth, this is notched, ductile, and that is notched, brittle. So for notched brittle, it will be sigma m by SUT by KF, right? Plus sigma A by SF by KF equal to 1. That implies sigma A by KF is equal to SF into 1 minus sigma M KF by SUT. Right? SF, yeah, sigma A by KF is equal to, yeah. All right. So this is my Goodman relation modified for ductile and brittle materials. Are there any questions?
Sorry, sir, but how did it become sigma A by KF? It should be KF into sigma A, right?
No, sorry, sigma A by no, sorry. I'm sorry. Sigma A times KF. Right? Is that clear?
Yeah, yes.
Sir, I just joined late actually. So why are we applying only for brittle material both look factors, sir? Actually, just
Yeah, because in the case of mean stress, you are actually talking about if it is a ductile material, right? If it is ductile material, SUT, by the time the stress reaches SUT, there will always be already some plastic deformation.
okay, sir.
Right? So that's why you need not account for that. But whereas if it is a brittle material, there is no plastic deformation whatsoever, and hence fatigue stress concentration factor will have significant influence on that.
Okay, sir. Got it. Thank you.
Yeah. Okay. So now let us look at fatigue crack growth. So we have looked at the fatigue stress concentration factor. Now let us look at fatigue crack growth. You are able to see my screen, I hope, with the slides.
Yes, sir.
Yeah. So what do we mean by fatigue crack growth? So let us carefully understand this figure. Okay. Here, what I am plotting here is the crack length as a function of number of cycles. On the right hand side, the stress or strength as a function of number of cycles. Okay, that means allowable stress as a function of number of cycles. Is that okay? Right? Now, let us say you have a component. When you are doing some test in the beginning, we know that there is no component whatsoever without any crack, right? Every component will have some crack, and your NDE equipment, non-destructive evaluation equipment's limit is what you suppose you are trying to detect the cracks in a material. You can only predict or detect a crack that can be falling within the limits of your NDE equipment. You cannot detect a crack smaller than that. Is that clear? That point, all of you agree with me? So now let us say you have a detectable crack length. every material will have a detectable crack length. That is this. Let us say this is my detectable crack length at 0 cycles, even before any operation of the machine component or any system has started. Now, corresponding to this crack length, there will be some strength, right, of this material. If you apply a much larger load, then that crack length becomes critical crack for that particular stress, but this is the stress for that. Okay. Now, as you increase the crack length, what happens as you increase the crack length? Suppose your stress intensity factor K, how is it defined? How is stress intensity factor K1 defined as?
Square root of pi A.
Sigma root pi A. Sigma is the applied
Sigma
stress,
root pi.
root pi A. Suppose if the crack is propagating, that means the crack propagates when K1 is equal to K1C, right? Fracture toughness. Now, let me, how do I do this one? So, we know K is equal to K1 is equal to sigma root pi A. This is for a system, let us say you have a crack like that, and if you are applying initial length of the crack is A, and if you are applying a far field stress sigma, some factor will be there, but that factor I am assuming it to be negligible. This is the sigma root pi A. When does this crack start growing? When K1 becomes equal to K1C. That is when crack grows, isn't it? So now, let us say you have some initial crack length. This is a crack length and this is number of cycles. And I also have on the second y-axis, I am drawing the applied stress sigma. Okay. So y-axis is second y-axis is sigma, and this one is that. Now, let us say my initial crack is that. That is what I call detectable crack length, AD. When will that crack grow? According to this formula, K1 is equal to, if I am applied stress is sigma root pi AD. When will it grow? When K1 is equal to K1C, right? K1C is equal to sigma root pi AD. Therefore, sigma is equal to K1C by root pi AD. Do you agree? That is what I call sigma critical. That means this is the stress at which the crack is going to grow. You all agree with that?
Yes, sir.
So, corresponding to that fellow, I am plotting. This is my, so that is on this side you have to see. Okay. Blue, that is sigma C. Now, as I am loading the specimen, this crack, as a fatigue loading, this crack increases its size. Let us say my crack is increasing its size. Like that. So at this point, sigma C is my critical stress at which the failure happens. If AD goes to say this, I am this point, let us call that point A1. What happens? AD went to A1, then sigma C will become will increase the corresponding stress, that implies stress at which crack propagates will happen what? Will reduce or increase?
Reduce.
Will reduce. So that means your sigma C, initially it was this, but corresponding to that, there will be reduction in like that, right? So as the crack is growing, as the crack is increasing, as the crack is increasing its length, what is happening to sigma C? Sigma C is decreasing. This is what we call residual strength of the material. As your crack changes its length, as it increases, the amount of stress that is required to be applied in order to grow the crack is going to reduce. So that is the point that I am trying to drive, and that is precisely what this figure is all about. Right? So as your initial some detectable crack length is there in the material, corresponding to the detectable crack length, you have some residual strength of the material, and the strength keeps reducing as your crack length keeps increasing. Okay. So let us say you have a component which is designed for n hat cycles. This is n hat cycles. At n hat cycles, if the crack is growing at n hat cycles, it will have certain crack length. Let us call that as a hat or whatever. Okay. And the critical crack length. So let us say the component is still subjected to the same stress, then the critical crack length is what? So this component is operating at n cycles, and the stress amplitude is, this is the service amplitude. That means when you are applying the load, this is the loading cycle that you are applying. Since your applied loading cycle is this, your stress, maximum stress is S max. It is never beyond S max. But the fact that you are actually doing this cycling, the crack length is increasing, and as a result, your strength of the residual strength of the material is decreasing. But still, the material is safe because the residual strength is much larger than the maximum stress that the material is experiencing. But as the crack length continues to grow, let us say there is a point at which the strength reduces to a value equal to the maximum stress applied through your loading cycle. And the moment you reach that, that is what we call a critical crack, right? Because your S max corresponds to the maximum stress amplitude that you are applying. And the strength cannot be less than that. If the strength of your component is less than that, then the material is going to fail. So until here, the strength is greater than that, and hence this point and the corresponding crack length is what we call critical crack length. So AC is the critical length, crack length reached from AD, where brittle fracture occurs if NIF cycles of loading has taken place. Now, if you are designing, if you have a system like that, so forget about, you have a system whose initially detectable crack length is AD. Corresponding to the detectable crack length, there is a strength associated with that particular material, that is this guy. But as you increase the crack length, imagine you are increasing the crack length somehow. As you are increasing the crack length, the strength is decreasing. Now, how is this crack length increasing? By doing some fatigue loading. But the fatigue loading is done in such a way that the mean stress is something and maximum stress is S max. And if your maximum stress that is applied is smaller than the residual strength of the material, then the crack will not catastrophically grow. Crack will grow in a stable manner, like what we are saying here. But the moment if your crack goes from AD to AC, at that particular point when it reaches AC, let us say the strength, residual strength of the component reaches the S max. X max is what? Applied maximum stress. This is the applied load. That is when catastrophic failure happens, because the strength becomes smaller than or equal to the maximum load that it can withstand. Now, if you, this is sort of your material response, right? A and SC. Now, if you have designed the component for enhanced cycles of life, you know this material, if it is operating with this kind of a loading cycle, it is safe until the crack length becomes AC, which can be computed by using the material properties until the crack length becomes AC. That means you can actually calculate. So that means corresponding to that AC, there will be some number of cycles, that is NIF. So the factor of safety in life, we have already seen NIF by N hat. N hat is the service that you have created. Similarly, factor of safety in stress at N hat cycles, the residual strength of the material is SC, but you are only applying a maximum stress of S max. So factor of safety in strength or stress will be SC by S max. Okay. Now the critical strength SC at any point is Kc by beta root pi A. So as the crack grows, as A increases, the critical strength of the material decreases. And failure occurs when SC reaches a maximum S max. So safety factor in stress due to applied cyclic load XC is equal to SC by S max. So sometimes the safety factors suggested by Xn and Xc are not sufficient due to a combination of unexpected detectable crack length and cyclic loading, and hence we need to do periodic inspection. Your safety factors Xc and Xn may not be good enough, and hence a periodic inspection is required in order to ensure that if you have a crack larger than AD, this is not suddenly growing, because you know this path and it is not supposed to grow faster. And you see the slope of this line is what we call dA by dN. A small slope, local slope can be, this is A and N, so this is dA by dN. Now, let us say in this path, your crack is growing. Now you need to do periodic inspections in order to repair. If you have a crack larger than AD, you always want to keep your crack much smaller so that it is not going closer to AC. So what you would do after some service, this is the actual number of cycles that the component is designed for. But in between also you do a inspection. Let us say this is the crack. Normally it would have followed this path. Now let us say after NP number of cycles, you have done an inspection and you found that the crack length has increased from AD to some value. Now what you can do? You can do some intervention and you can do some repair such that the crack can be closed. Then what happens? Again, the crack length, which was increased from AD to some A0, A1, can be further reduced and then reduced to AD. Because you cannot reduce below AD because AD is the detectable crack size. Below AD, even if you reduce, you may not be able to see. So the best bet is you can reduce it to AD. The fact that you have reduced it to AD, you can see that the strength has reduced as the crack length increases. But the fact that you have done the intervention, so this guy will increase again to same value. Like that, if you do this periodic inspection, whenever the crack length increases at every NP number of cycles, you can do the repair and improve the life of the component as long as you want. So now, in order to talk about this fatigue crack growth, we have, this is Paul Paris, who actually talked about this fatigue crack growth. So rate of crack growth, that is dA by dN, as a function of plotted against the stress intensity factor range. What do we mean by stress intensity factor range? If you look at this fellow, the stress is cycling, right? This is what we call delta sigma. But delta K is equal to sigma root pi A. So delta sigma will be delta K will be delta sigma root pi A, because K is sigma root pi A. So delta K will be, that means stress intensity factor range will be delta sigma root pi A. That means this range. So if you would plot dA by dN as a function of delta K, this is how the plot looks like. It shows a sigmoidal behavior into three regions. The region 1 is what we call initiation range. Region 2 is typically your crack propagation stage, and region 3 is unstable fracture. That means that is when you are reaching this fellow. Until then, you have a stable crack growth. Okay, so region 2 is mostly of interest for us. This KTH, delta KTH is what we call threshold stress intensity factor, because you will not have 0 delta K, because delta K, delta sigma root pi A, where A is your detectable crack length, and that will tell you delta KTH, right? Otherwise, the crack does not grow. If your stress intensity factor is less than delta KTH, the crack will not grow, crack remains the same. Only when you have some threshold value, then the crack starts growing. And initially, it will initiate in this region, crack gets initiated, and this 2 region is where the crack growth happens. And you see that dA by dN as a function of delta K shows a straight line on a log-log scale. It is not a normal scale, it's a log-log scale. So on a log-log scale, you can say that it's a straight line of constant amplitude. So that is power law in some sense. So you can write dA by dN as C delta K whole power m. You can clearly see a nice linear fit, and here the threshold delta K, and here it is suddenly breaking. So initial step, steep region at low delta K values, there will be no crack growth. That means there isn't enough stress intensity factor. And then you have a stable crack growth. And finally, the crack has grown to such a large height, then suddenly it will break open. So we are actually talking about the Paris law talks about crack growth, fatigue crack growth, that is in the region 2. So the region 1, there is no crack prior to this delta KTH. And then this is a stable crack growth region, that is region 2, and that is our unstable crack growth region. So the part of the curve in region 2 is what we call straight line, is a straight line on log coordinates, and that is found by Paul Paris. And this is what we call Paris law, dA by dN is equal to C delta K power m, where C and M are your fatigue material constants, which can be obtained through experiments. So if you integrate this equation, you can find out fatigue crack growth life. And for many materials, for steels, M equal to 3. And for aluminum, it can be between 3 and 4. But C depends on different materials. M is more or less, for steels, it is 3, and aluminum, it is between 3 and 4. So region 1, we did not talk much about this region 1, but that is also interesting, as it shows the threshold limit, below which there is no crack propagation. So if your K delta K, if you compute, if it is less than this delta KTH, then you need not worry. The crack will not grow in that region at all, right? So usually delta KTH, that threshold stress intensity factor, occurs at a very small propagation rates, 0.5 nanometer per cycle. That is why you don't see the crack growing. Although the crack may be growing, it is growing at a very small rate. That is why it is called crack initiation stage, not a growth stage. And region 3, that is your unstable crack growth, this is your region 3. So where the K max, the maximum stress intensity factor value, becomes Kc, fracture toughness, that is when there will be unstable crack growth. So now, what is the effect of mean stress? Here again, delta K we are talking about, but we never spoke about whether it is mean stress effect or not. So what happens when you have a mean stress? So normally, if you don't have mean stress effect, that can be written in terms of stress ratio R. With 0 mean stress, what is the stress ratio R? What is stress ratio in the case of mean stress? -1. If it is -1, so 1 plus 1, 2. So C2 delta K whole power M2 by 2 Kc minus delta K. All right. So that somehow breaks down to dA by dN is equal to C delta K power M. Okay. That you can find out, but this is the influence of the stress ratio if you have mean stress. If you don't have mean stress, you can use this formula, C delta K whole power M. Otherwise, you can use this Foreman equation. Okay. So this is how do you obtain crack growth behavior? and using for applications. How do you apply? So for example, if you have a specimen whose dimensions are such and such, and then you are applying a cyclic load. So the load is going between P min and P max, and this is what we call load range delta P. So now let us say you are applying different delta P's, delta P1, delta P2, delta P3. If you have chosen delta P1 to be larger than delta P2 to be larger than delta P3, if for larger delta P, the crack growth rate will be higher. That is expected, no? Because you have a larger delta P range and hence crack grows faster. That is why that is why we call dA by dN will have higher slope. Okay. And delta K, you can compute delta K is equal to delta P by T root B FP. This is delta K is sigma root pi A. Very similarly, for this particular specimen with a rectangular cross section with distance B, double single edge notch specimen, this distance being B, this crack length initially going to be A and then T. This A from this position can be computed, and then you would be able to plot this delta K and dA by dN as a straight line. Okay, on a log plot. And now in a laboratory, what would you do is you, instead of load, you call it a stress because you divide it with area. All right, and then if you do this test, and then if you in the actual application you measure the stress, and for different stress amplitudes, delta S1, delta S2, delta S3, you know that a higher stress amplitude will result in faster force, and then from there you can calculate delta K is equal to some beta times delta sigma root pi A. That is, you do the laboratory test and generate this curve, and then from the actual application you calculate delta K, and from that delta K you look at it and then find out what is dA by dN. That means crack growth rate. Okay, so let's look at this particular problem. You have a mild steel plate subjected to a uniaxial fatigue load to produce varying stresses from sigma max 180 MPa to minus 40 MPa. The static properties sigma naught being your yield strength of the material, SU is ultimate strength of the material, elastic modulus, fracture toughness Kc. If the plate contains an initial through thickness edge crack of 0.5 mm, like what we have seen here, initial through thickness edge crack of 0.5 mm, how many fatigue cycles will be required to break the plate? Assume an infinite width plate for which beta equal to 1.12, Paris law C equal to 6.9 to 10 power minus 12. Because it is steel, Paris law constant M can be taken as 3. Right? So let us get started. How do we go about solving this problem? I will just copy the problem here so that you can. You're able to read the screen now?
Yes, sir.
Yeah. So now let us look at how do you go about solving this problem. So what is that we need to find out? The question is, how many fatigue cycles will be required to break the plate? Right? So you have some loading scenario. So this is 180 MPa and sigma min is 40 MPa. Right? This is sigma max and that is your sigma min. Okay. And SUT sigma y is equal to 500 MPa yield strength. Sigma UT or SUT is equal to 600 MPa. Right? What is the initial crack length?
0.5 mm.
So how do you find how many cycles are required? What will be the critical crack length? You should know what is critical crack length. We don't know, but we know fracture toughness to be 100 MPa root meter. Correct? So we know Kc is equal to beta, that is geometric factor, sigma root pi AC. With this sigma will be sigma max, the maximum stress that you are applying, right? So therefore, AC will be equal to Kc by beta sigma max whole square divided by 1 by pi. So that is equal to 1 by pi. Kc is 100 MPa root meter, right? Beta is 1.12 and sigma max is 180 whole square, right? What is that? 180 MPa, this is MPa root meter, so this will come in meters, right? How much is that coming to be?
I'm getting around 0.078, sir.
0.078
078.
meters. That means how many mm? Wow.
78.
How much?
78 mm, sir.
So critical crack length is 78 mm. So we know initial crack length is this. When this initial crack length becomes 78 mm, that is when failure happens. We are asked to find out how many cycles that does it take to reach there. So using Paris law, I know, what do I know about Paris law? That is the Paris
Integral.
law, right? But this is when there is no mean stress. What is the mean stress here, by the way? In this case, sigma m is equal to 180 plus 40 by 2.
70.
110.
Sorry, 70, right? It is minus 40.
Yeah. So what is
Sigma m should be 70.
Is it 110 or 70?
70 MPa?
Okay.
So somewhere here. Okay. So now, if you K max is 180, if you look at this fellow and K min is K max 180 root pi A, K min is minus 40 root
Yes.
pi A. But K min is negative. So in order to give negative side, we will not have any crack growth, right? So and hence it should add some life. But in order to do a conservative estimate, you can assume K min to be 0, right? So delta K in this can be K max minus K min, where K min can be considered to be 0 if it is less than 0. So what will be K max? That is equal to beta times sigma max root pi A. Do you agree? Delta K is equal to that. So I can write dA by dN is equal to C times beta sigma max root pi a whole to the power m. Now, if I integrate both sides, right, what will happen? dA divided by C beta power m sigma max power m root pi whole to the power m, right? 1 integral A initial to A final dA is equal to integral 0 to number of cycles to failure dn. Can I do that?
So what happened to a power? I mean, square root of a power m.
This will become dA by root a power m. Sorry. Thank you. Correct?
Yeah.
So now I know what is C. What is C value? 6.9 into 10 power minus 12. Beta is 1.12 whole cube because m is equal to 3. Sigma max is 180 MPa whole cube, root pi whole cube, and root a power m is?
Is that initial crack?
No. A power m, we have to integrate it, no? dA by root a power m means a power minus m by 2 plus 1 by minus m by 2 plus 1. Integral x power n dx is equal to x power n plus 1 by n plus 1. If it is limits
All right.
x0 to xf, then we will do x0 to xf. Correct?
Yes.
Yeah, so the same thing applies here or not? So this can be written as a power minus m by 2 dA ai to af is equal to nf, because integral dn is n between 0 to nf, so that will become nf. Agreed?
Yes, sir.
Now, whatever this number is, you will compute. And this one will be whatever this number, I am calling it as a times a power minus m by 2, that is 3 by 2, 1.5 plus minus 0.5, right? A power minus m by 2 plus 1 divided by minus m by 2 plus 1. Between limits ai to af is equal to nf. That implies number of cycles to failure is equal to a times capital A times a power m is equal to 3 by 2. Minus 3 by 2 is minus 0.5, minus 1.5 plus 1, that is minus 0.5 divided by minus 0.5 between limits ai to af. What is ai? That is
Initial
AF.
crack,
So
0.5.
minus a by 0.5, I can bring it out. So AF, that is AF is what? What is the failure AF?
Critical
78.
crack.
78 to the power minus 0.5 minus
0.5.
actually I should not say 78 because it is all done in meters. So 0.078 minus point
I mean, 5 to 10 power, 5 to 10 power minus 3.
5 into 10 power minus 3 whole power minus 0.5. So what is that number? Okay, if you do that computation, you should get something approximately 261,000 cycles. Just do the computation and tell me whether that is the number that you are getting. Okay, did you get that?
Sir, I am getting different one, but I don't know why.
You are getting a different number. What is the number that you are getting?
So 67,139 cycles I am getting.
So me
Okay.
too. So 67,000.
Everyone is getting the same number? What? 78 mm. So what is the C value that you have taken?
6.98 10 for minus 12, sir. It is given.
A minute, let me check.
Sir, I'm also getting different number actually.
What is the number that you are getting?
150,000 cycles something.
Each one is getting a different one. No? C is equal to 6.9 E minus 12. M is equal to 3. Equal to 6.9 E minus 12. M is equal to 3. A0 is equal to 0.5 mm, right? AF is equal to
A value, is it 3176? A value?
3176.
A value I'm
Yeah,
getting 6357.
Yeah, altogether.
altogether A value is 3176, correct?
Okay. Capital A value.
Capital A
Yeah,
value.
capital A, yeah.
Capital A is equal to 1, 1 minute. Sigma max is equal to 180. 6 MPa. Okay. Now, $78 mm, 78. Okay. Now let me see. A is equal to 1 by C star. Beta is how much? 1.12.
Yes, sir.
Beta 4 beta star max star A is how much?
3176.5.
3176.
3.
3176.54.
Are you taking 180 or 180 MPa? MPa is, are you taking them in the consistent unit?
Yes, sir. I think 180. Yes, I have taken wrongly. I mean, like
Yeah.
it is MPa means Newton per mm square. So
MPa into 10 power 6 Newton per meter square is what you need to take. Right? A, how much you have to tell me?
three point 176 into 10 power minus 15.
Okay.
Sir, I'm not getting this number.
So, did you get any meaningful answer?
No, sir. The cycle I'm getting.
Hmm?
I'm getting 6.7 into 10 power minus 14. Not this number.
Yeah, sir. Only the decimal will be changing, right, sir? Right.
So, what is the number of cycles that you are getting? Not 261,000, but what is the number?
6.7 into 10 power minus 14.
That means 0 cycles.
0, yeah.
So that means there is some problem in the way that we have applied the formula. How do we figure out?
So we'll try this as a homework and maybe we'll.
Yeah, you please try this and then ensure that your numbers are meaningful. Okay. Okay. So I think so that's sorry. That's what you will do in the at home. You please figure out where we are doing mistake in this calculation and then find out the answer. Okay. Or if you want, you can write a small MATLAB or whatever code that you want, because if the the equations are cumbersome, you can do that and then find out. Okay. And now the next thing that we need to go about. So far, we have looked at stress life approach. In next, we need to look at strain life approach. So in tomorrow's class, we will look at strain life approach. And then on third, we have the last class, right? When is our last class?
9th, sir.
9th, okay. So tomorrow and day after tomorrow, we will look at strain life approach. And then if day after tomorrow, we might also start creep. So now I have a question to you. Do you want to study creep or you want to study polymers? It is up to you.
Creep. Creep we can do it, sir.
Creep is better.
Yeah, sir.
Okay. So then I will, all of you are okay with that creep?
Yes, sir.
Yeah. Can you please, yeah. If everyone votes for creep, I will go with creep. Otherwise, I will do polymers.
Sir, our match is okay with creep, sir.
Okay. All right. Fine. So we will do creep. And then most likely in tomorrow and after tomorrow, the strain life approach is little bit more involved. You need to understand plastic deformation. So we have already discussed what is plastic deformation all about. And we will go a little deeper and talk about this concept of Boschinger effect and so on. And then we will talk about the strain life approach, because that is where plastic deformation is involved when the fatigue loading is applied. Okay. So that is, we will start and then try to see how we can apply the fatigue failure theories for low cycle fatigue, where the stress is expected to be very close to the yield strength of the material. All right. So I think we'll stop here and then we will meet tomorrow with the new topic. All
Sir,
right. Thank you. Yeah.
Sir, I have a question, sir.
Yeah.
As the final exam is nearby,
Mm.
sir, the weightage will be more after the midterm syllabus, or how
So
is
I
it?
will not have the first module like crystal structure, mechanical properties will not be there. Only failure theories and creep for the exam.
Okay, sir. Yeah,
Great,
thank
sir.
you, sir.
Great, sir.
Thank you.
Yeah.
Thank you, sir.
Okay.
Sir,
Yeah.
thank you so much for this kindness. Thank you so much.
Yeah, no problem. And
Thank
you, sir.
I hope you all have got access to your answer scripts.
Yes, sir.
Yes, sir. Yes, sir.
Yeah. Okay. All right then.
Sir,
Day
sir,
after
one more,
tomorrow,
sir.
there is, I mean, for the other course, I think we have a presentation, I guess, for day after tomorrow.
When? Day after tomorrow.
Yeah, Wednesday.
Until what time? Up to what time?
No, we don't have that.
We don't
actually.
have. We don't
Oh,
have.
we don't
Sorry. It's on 4th.
Sorry.
We don't have on 3rd.
You know,
Okay, sorry.
Yeah.
Sorry.
Okay. Both the batches are available, no? Tomorrow, day after tomorrow as well.
Yeah, we are available. Sir, only one. Sir, I have submitted my assignment through mail also, sir.
Yeah, I got it. I have sent to the TA. Okay.
Okay.
Sir, can
Thank
you
you,
send the mark distribution? What was the average score, or what is the highest score, or something?
I will tell you. I will have to look at it tomorrow. I will look at it and then let you know. Okay.
Okay, sir. Thank you very much.
Okay.
Thank you.
Bye.
Thank you, sir.
Bye.
Thank
Bye.
you, sir.
Thank you, sir.
Thank you, Prof.